So now that we have all the tools in place for exploring random variables, now let's actually talk about some really cool models that we can use that use random variables and their distributions to model the probabilities and how we can answer questions about these random processes. So as an example, we'll talk about prevalence. So to refresh your memory, prevalence or prevalence risk is the probability of a selected person of having that illness at that given point in time, if it's point prevalence, or over a certain period. So 10-year prevalence would be over the duration of 10 years, what's the probability of them getting that illness? And the important part here is that we don't know, or it's random, because we're selecting at random from a population. So to motivate this, then, we'll talk about hypertension. And this is a very common condition that is also known as high blood pressure. Yours truly has high blood pressure. And in fact, you probably know quite a few people who have high blood pressure. It's exceedingly common in the United States. It's a condition that causes increased and sustained force of blood against your artery walls. Over time, it can lead to heart disease and strokes. So it's a chronic illness that somebody can have either the early stages of it or an advanced version of it, or not have it at all. But we'll lump together the early stages of hypertension and the more advanced versions and just call it hypertension or high blood pressure. And according to the CDC, so this is data from the CDC, this has a 33.2% prevalence among 40 to 59-year-olds. So from the general population of people aged 40 through 59, 33.2% of those, let me rephrase that. If we randomly select somebody from this population, they have a 33.2% chance of having high blood pressure. So why don't we, for example, take a sample of size 6. So we'll take 6 people from this population. And because this population is in the millions, we are not, it is not terribly important whether we select with replacement or without replacement. So as long as, and this is an aside, as long as your sample size is much smaller than your population size, with or without a replacement doesn't matter. It's the same. So our main question in this video is going to be, how do we interpret, or how do we understand the distribution of random variable x, which is going to be the number of people in the sample, who have hypertension. So to understand this, let's just draw it out. So we have, whoops, that person's not supposed to be upside down. We have 6 people, all from the same population, possibly the same person or not. And what are the possibilities here in terms of how many people in the sample have hypertension? Now, we don't care about which specific person has hypertension, so we just care about how many do. So it could be these 2, so in which case x equals 2, or it could be these 2, and then again it would be x equals 2. So that part doesn't matter to us. All we care about is how many people in the sample. So order doesn't matter here. In short, we're interested in combinations, not permutations. Okay. Similarly, or I should say, in addition to this, for each person in the sample, they have the same probability of having hypertension as every other person. So for each person, they have a probability 0.332 of having hypertension, which means they have a probability 1 minus p 0.668 of not having hypertension. There are no other outcomes that we're interested in. We're just interested in whether they have it or whether they don't. So yes or no. Have it, don't have it. It's a binary, right? Lastly, each person has the same risk of having hypertension independent of whether other people in the sample have it or not. So we're not assuming then that we're literally putting these people in the same room and that they have the same habits or that they have any connection to each other, right? If this were an infectious disease, then we would not be taking them in consideration in terms of, oh, well, now we've put them in the same room, so now there's a possibility of spreading the disease. We are observing each person in their own hyperbaric chamber, as it were. So now that we understand that, how do we actually start to put together things about this distribution? So what's the support? So our sample size is 6, which means x can take on values from 0, that means no people in the sample have hypertension, 1, in other words, just one person has hypertension, 2, and so on. And the very last possible outcome is all 6 of them have hypertension. So this is our support. So none, 1, 2, and so on. And the last one is all of them have it. Now we expect that if we have a 33.2% prevalence, that's probably not going to make it so that it's likely that all of them have it. That'd be very unusual, right? So let's look at the extreme cases first and use this to try to figure out what the probability mass function should be. So case 1, what's the probability that no people in the sample have hypertension? So each person then, what we're saying is each of them has doesn't have hypertension, so we're interested in the 1 minus p chance of not having hypertension, and this happens independently 6 times. In other words, if we were looking at a probability tree diagram, we'd be looking at the branching, so it'd be something like a branching off into 2 each time. For each stage corresponds to a different person in the sample having or not having hypertension. So it's a binary tree for a probability tree diagram, and as you can tell, I've already made it so that it's very hard to represent all these outcomes at once. But if the top branch is all the yeses, and the bottom branch is all the no's, then we can figure out directly, which is tedious, but we can, all the possible outcomes of obtaining or not obtaining that, of having hypertension. So remember, if the top branches are all the yeses and the bottom branches are all the no's, then we have 0.332 and 0.668 for the first branching off. And then the next one is also 0.332, 0.668, and so on, all the way down until we get to the very last stage. So this means if we're selecting the case in which none of them have it, we're actually looking at this branch, which means if we trace down all those probabilities, we're using the multiplication rule now. And so we get 1 minus p to the 6th power, which is your 0.668 raised to the 6th power, which is roughly, and I'm approximating now, 0.0889. So the probability that none of the people in this sample have hypertension is roughly 8%. Case 2, which is the other extreme, what's the probability that all of them have hypertension? Well, that'll be the exact opposite, which will be the top branches only, and so we actually get p to the 6th, which is 0.332 to the 6th, and that's roughly 0.0013. So this is even more unlikely than none of them having hypertension. So does this make sense? Since it's more likely for any one person to not have hypertension than to have it, it makes intuitive sense that it's more likely for none of them to have it than all of them to have it. So let's check one more, just so that we can come up with a general form for this probability mass function. So case 3, we're going to find the probability that exactly 2 people in this sample have hypertension. Now, if 2 of them have it, then that means let's look at our representative branch. So let's suppose we're looking at the branch in which the first 2 people have it, and then all the rest of them don't. Now, that doesn't necessarily mean that that's the only branch that's possible. In fact, any branch that has 2 people who do have it and 4 who don't will be part of this event. So in that outcome, we have an inclination that we should have 2 people who have it, 4 people who don't. So we have this factor of p squared times 1 minus p to the 4th, and that's representing those probabilities. So that's that branch. But since we need to account all the possibilities, we need to count all these combinations. Remember that in the beginning we said we are interested in combinations, not permutations. So one way to think about this is think of the group of 6 people, we're choosing 2 of them, and those are the 2 that have hypertension. So in other words, this binomial coefficient, 6 choose 2 times 0.332 squared times 0.668 to the 4th, which is roughly 0.3292. And that actually makes sense. So 2 out of 6 is roughly 1/3. And if the point prevalence of an individual having hypertension is roughly 1/3, then it makes sense that this is a much more likely outcome than the other outcomes that we observed. In the next video, we're going to actually classify all these different kinds of examples based on the commonalities that we found in this example and find out what the general form of the probability mass function is going to be, and that will allow us to then answer a lot more interesting questions about not just prevalence, but any kind of model that is similar to this particular example and having the same commonalities in terms of random processes.